So what we're going to be doing in this video is we're going to be talking about taking derivatives for functions of more than two variables. So we had a lengthy discussion about taking partials with respect to two variables, like we've got a function f of x, y, and taking the partial derivative with respect to x and the partial derivative with respect to y. What we're going to be doing now is just talking about, like, what if you have a function of three variables, all right? So basically, you know, we've got f of x, y, z, or even really, if you've got a function of more than three variables, okay, 5 variables, 7 variables, it doesn't matter. The process is essentially going to be the same. And it's going to be the same as if it was a function of 2 variables as well. What we're going to do, and you can kind of see this here, is we're going to be basically holding, we're going to take the derivative with respect to one of the variables and then hold all of the other variables constant. Okay, we're going to hold all the other variables constant. So you'll notice, like, say for example, in the case of this first derivative, we've got x plus h to x, but then y and z, they're going to remain constant. They remain the same. When we look at the df dy, we are going to be changing y plus k and y, right? So we're going to be looking at the change in y, but we're holding x and z constant. And then when we look at df dz, we're going to be holding, we're going to be taking the derivatives with respect to z, okay? Like what happens to f as z changes, and we're holding x and y constant. And so really that's just basically the concept. That's the concept that we're going to be working with whenever we take partials. It's also going to be the concept when we talk about second partials. And when you take second partials with respect to, like, variables with, functions with lots of variables, things get a little bit more crazy. Right? Basically, like, instead of, say, for example, 4 sets of partials, you have 9, right? Because you've got, you know, xx, xy, xz, yy, yx, yz, zz, zx, zy, okay? And so you can imagine that it just starts to multiply quite quickly if you think about all the different kinds of partials that you can possibly take, all right? But the concept is still exactly the same. There's no difference. There's no change in the concept. So let's see how this is done. Let's suppose that we have a function like this. F of xy equals x squared y minus 4xz plus y squared over x minus 3yz. And you might look at that and you go, oh, it's gross. It's got, like, quotient rule in there. It's got all those variables. It's got x's and z's. But remember, like, a ton of them are treated as constant when you take the derivatives. So let's say, for example, I take fx. Okay, so this is going to be df, and this is xyz, pardon me. xyz. So fx, so we're going to hold y and z as constants. Okay, so we are going to use quotient rule, which is fine. So we're going to take the derivative of the top part, the derivative of our top. So that's going to end up being 2xy minus 4z. Okay, and then the y squared, there's no x's in that, so it's constant, so it goes away, it's a 0. All times x minus 3yz. Then minus, and if you take the derivative of the bottom, that's just 1. Okay, because 3yz has no x's in it. So it's going to be 1 times x squared y minus 4xz plus y squared. And then we'll just divide through by x minus 3yz squared. Okay? If I were going to go in here, I mean, you know, let's just actually go in. We'll do some simplification for a little algebra review. We got 2x squared y minus 4xz minus 6x y squared z plus 12yz minus x squared y plus 4xz minus y squared. All over, and let's just keep this at x minus 3yz squared. Okay? I think maybe on the next one we just won't do the algebra. But for this one we did. So we've got, there's an x squared y, there's an x squared y. So this ends up giving me x squared y. Okay? And then I have minus 4xz plus 4xz. Okay, so that's 0. They cancel. Okay, so I got minus 6x squared xy squared z. All right. And so that's the only one we got like that. And then plus 12yz. And then minus y squared. All over x minus 3yz squared. That's just a little algebra. This part here, right, that's the big derivative part, okay? And that's all we got to do. Let's take a look at fy. look at Fy. We'll go back up to that the first equation, and then now we're going to take the derivative with respect to y. So this is going to be just x squared, because x squared is treated like a constant. The derivative of y is 1 with respect to y. Minus 4xz has no y's in it, and then plus 2y. Okay, again, we're back up here. It's plus 2y. And then we'll multiply that by x minus 3yz minus, okay, and this is now, that's just going to be negative 3z, right, because z is considered constant, so minus a negative 3z times x squared y minus 4xz plus y squared all over x minus 3yz squared. And there we go. Now let's do fz. So fz, we look, only the middle term in that top part has actually a z in it. So that's going to be just negative 4x times x minus 3yz. Then minus, and now this is going to be a negative 3y, right? Because 3y, z, derivative of z is 1. 3y is considered constant. And then times x squared y minus 4xz plus y squared. All divided by x minus 3yz squared. That's it, right? Rules remain the same for our work as we're working with our partials. All right, just the difference is that depending upon the variable that you're taking the derivative with respect to, the other variables will be considered as constants. And that's it. That's really all I wanted to go through when it comes to finding these partials for functions of more variables.